started?
No.
No.
You don't. All right.
Not yet, Vijay, no.
Oh, yeah.
Yeah.
No.
Yes, I think it's come on. There's a bit of a lag. Yeah. Okay. Right then. Catherine, the floor is yours.
Okay, thank you very much, Vijay, for the introduction. So let me try and get my slides to share. And here we go. So hopefully you can see those slides this morning. Okay, so yeah, I'm Cath Noakes from the University of Leeds, and I'm going to start this webinar by talking about what we know about transmission and thinking about what that might mean in terms of mitigation measures. So, I mean, some of you may have seen a diagram like this before, but it just to illustrate that actually, although airborne is one of the mechanisms of transmission, we can't be sure that that's the only mechanism. And I think we have to be aware that this disease quite possibly transmits through more than one route. I mean, the virus is in respiratory droplets in people's exhaled breath. Those can be very small and stay as aerosols in the air and be inhaled by somebody. But there are also, we do know, much larger droplets which potentially either can deposit directly onto mucous membranes, so in your eyes, nose or mouth, or potentially land on surfaces, and we can have transmission through contaminated hands. So even though that looks like it's probably a smaller route of transmission compared to the direct exposure to droplets and aerosols, we can't discount it yet. So I think bear in mind, first of all, that actually the routes of transmission are uncertain. But there are a number of things that we have learnt over the course of the past 15 months or so. So we do know that as you're closer together, the risk increases. So we know there is some good evidence that suggests that proximity is a major risk factor. Enclosure, being indoors, we also know that's a major risk factor. And we do know that poor ventilation is associated with certain, particularly super spreading type outbreaks. As with all of these things, duration matters, and I think that's probably a probability thing, in that the longer you are close to somebody, the longer you spend time in a space where there's an infectious person, the greater the chances that you will be exposed to the sufficient virus to cause infection. We know as well that there are certain activities that make transmission more likely. Singing seems to be quite a major risk factor. We've had a number of outbreaks associated with choirs. And the same breath, loud speaking, both of which generate more aerosols from the human respiratory tract. But we also know that aerobic activity matters too. And I think there are two factors in there. One is that if you're the infectious person, you generate more virus when you're doing aerobic activity, but also your breathing rate goes up and the breathing rate of the susceptible people goes up, so they can breathe in more virus. And it seems to be, again, aerobic activities in indoor spaces, so particularly high impact gym classes and things. More people in environments actually means there are more chances of an infectious person being there. We know a bit about the environmental conditions, so we know that the virus prefers cooler temperatures. It prefers drier conditions, so there's a greater risk at low humidities. And it survives better in dark compared to bright sunlight, where the UV will inactivate it quite quickly. What we don't know is how much these factors matter compared to some of the other factors. And then the other challenge I think we have is the symptoms. We know that a lot of people before are asymptomatic or pre-symptomatic, so they've had very little symptoms before they transmit it. And that means you don't have to have a cough, you don't have to have a fever. People are transmitting it without knowing they are transmitting it. How do we know some of this? And I think this is really important. We do not have a definitive way of determining how transmission happens and which mechanisms and which factors matter the most. And we also don't know whether, even if we did measure it in a particular environment, whether that translates to every other environment. We think possibly not. We think actually that the transmission routes might depend on the activities and the environments that people are in. We have to try and pull the evidence from transmission from multiple different sources, and all of them are incomplete, all of them are uncertain. So again, we have to be really careful that we don't just see an outbreak that's associated with a poorly ventilated space and go outbreak, ventilation, that's it. There are multiple factors that we have to take into account. So in order to understand this, we're looking at animal studies. So we can use animal studies. Hamsters particularly apparently transmit this disease very well. We can look at that, shows us that we know that it can travel through the air and that it potentially travels on surfaces too. But hamsters aren't people, so we can only translate that so far. We get a lot of information from outbreaks. We can identify whether there are common features in those, what sorts of interactions happen. But we have to remember that an outbreak is the thing that has been identified as a cluster. It doesn't necessarily represent the background day-to-day transmission that's clearly happening in a lot of places. There's an awful lot of information we can get from things like contact tracing data. There's a huge wealth of information in there. But again, we have to remember that that data is not set up to measure transmission. It was set up to contact people and manage the pandemic. So it has its limitations. But from that, actually, we can see that when people are closer together, the risk goes up. It's about twice as risky when people report very close contacts to when they report just sort of 2-meter contacts. We can also identify from things like that which types of venues and activities are associated with transmission. Again, we have to be careful not to immediately say, okay, a case happened in a gym, therefore gyms are dangerous. It doesn't quite work like that. And there are plenty, we also have to bear in mind that many venues have been closed, so we don't know what transmission's like there. And then there are many venues where it appears it's associated with transmission. So for example, if you ask people who've got the infection what they did over the past week, huge numbers of them will say they went to the shop. Well, that's not that surprising. So it's not surprising that shops come out high on the risk factors, but that doesn't mean they necessarily got that infection in that shop. Increasingly, we're able to use genomic data, which is fascinating, but allows you to look in detail at the connections between cases. And sometimes you have an outbreak which looks like an outbreak, but there is no genomic connection between the virus strains in there. And therefore, that means actually it wasn't. It was just chance that those people were in the same place at the same time. And we can start to get data by looking at things like cohort studies, case control studies to follow people through. These are hard, though. You have to follow lots of people. In terms of interventions, the population scale data tells us about the major interventions, tells us about things like if we close schools or if people work from home. It doesn't tell us anything about things like ventilation or hand washing or masks. It tells a little bit about masks, but it's very hard to pull out those sorts of interventions. We have people who've sampled the environment. If you sample the environment in a hospital, which has got COVID patients in it, you can find it in the air and you can find it on surfaces. If you go and sample a workplace, the chances are you will not find anything. And that's because you will only find it in the air if somebody infectious is in that environment at the time or was there very shortly beforehand. And you might find some traces of RNA on surfaces. That means that somebody infected was there, but they could have been there 3 weeks earlier. We don't know. So it tells us something, but not as much as we think it should. And then we have a lot of data from laboratory type settings. So understanding the physics of aerosols, the survival of microorganisms in a lab. Again, we can use this to infer things, but we have to be quite careful. These are often models. They're not representing real life. And as with most models, you can tweak them to make them do what you want. So we can use them to inform where we think we should look, but we have to be careful of saying the model says this, therefore it's a risk, because that doesn't quite work either. Let's just think through the transmission dynamics. We're starting with a respiratory source. That might be breathing, coughing, talking, sneezing. It might be when somebody's undergoing treatment. That source is respiratory virus within liquid droplets or aerosols. It will have a size distribution. It will also have a location. It will have a duration. We can't just assume that somebody is exhaling this continuously. It might change and vary through the day. Once it's in the environment, those particles are transported in the environment, they deposit in the environment, and cause an exposure to somebody. That exposure will depend on how close somebody is, but you'll have the long and short range aerosols which are inhaled, the larger droplets which are deposition and give you contact, and then the surfaces and fomites. And understanding this, we need to think about the microorganisms, the human characteristics, and the fluid dynamics of that environment together. First of all, thinking about the beginning of that, where is the virus? So our exhaled particles range from less than a micron to over 1 millimeter in size. So a huge range in our exhaled breath. The virus is much smaller. It's 0.1 of a micron or 100 nanometers, but it's not a naked virus. That virus is contained within a respiratory fluid, and that respiratory fluid isn't water. That contains salts, proteins, surfactants, other microorganisms. So although those particles evaporate, they don't evaporate to just a naked virus. They evaporate to this sort of concentrated soup of virus and other things like salts and protein. We think that there are more viruses in bigger particles. We don't know that for sure, but I think it's a reasonable assumption with this virus. So the big droplets are probably containing a much higher punch of virus than the very small particles, but the smaller particles are more numerous in nature. And we can inhale up to 100 microns. Below about 5 microns can get in the deep lung. And just to explore this, just thinking about size, imagine this is our 100 micron droplet. The width of a human hair is about 60 micron. The human eye can see down to about 40 micron. This would be a 10 micron droplet, so we can't see it. And here's our 1 micron droplet or aerosol. It would be tiny, and I can't actually put the virus itself on this page because you wouldn't be able to see it. It'd be too small. So the scales involved are orders of magnitude in variation, and that's one of the things that makes it very challenging to understand this. This size matters though. These really tiny aerosols, less than 10 microns, they might start life bigger, but they evaporate really rapidly to become these small ones. They'll hang in the air a long time. We produce lots of them, but they carry quite a small amount of virus. They provide a danger when we're indoors, but when we're outdoors, they provide much less danger because those are the ones which can get really easily dispersed by the wind, and it's very unlikely we'd breathe sufficient of them to cause infection. The medium-sized aerosols, so the ones that are sort of, I guess, between about 10 and 100 microns, and some of them might start slightly bigger and they evaporate to these, they deposit relatively quickly, but will stay in the air for, some of them, for several minutes. We do produce less of this size, but we know they carry more virus. We actually think this size is probably quite dangerous. These are the ones where when you're close to somebody, they stay in the air long enough that you can inhale them, and they probably carry enough virus to cause infection. So these are the ones that are quite possibly the biggest risk, but we think those tiny ones matter too. The very large droplets deposit quickly. We produce quite a small number of them. I've got noise on the thing. If people can mute their mics, that'd be great. Thank you. We produce very few of these, but they can carry a lot of virus. So I think if you get hit in the face by one of these, it possibly causes a danger. But it's again the probability that you will be hit by one of these really large droplets, and it's quite a small probability. Let's talk about activity. So I mentioned activity matters. These are just some particle measurements. This isn't virus, but this is particle measurements from people doing different respiratory activities. And I want to note two things in here. One is that singing and speaking, when people get much louder, the number of particles they produce increases. So we can see there's a relationship there. But I also want to show breathing. If you look at breathing, you can see there is an enormous range. I think this is 26 people. And some people breathe out almost as much as other people produce when they're singing. Others produce a lot less. So we can't assume that everybody's uniform. There is a huge variation between individuals, and that we need to take into account in here. And on top of that, the viral load matters. So the graphs shown here, the one on the far left shows the the virus SARS-CoV-2 compared to an influenza, which is the blue line. And what you can see is these are in log 10 copies, but it varies by probably 8 orders of magnitude or more between different people. And the same is true on the one on the right. This measures it in something called a CT value, but it's a huge variation in orders of magnitude. But what we do know, the one on the right shows us that we get the peak is prior to symptoms being reported. So we know that the people's viral load is at its peak around about the time just before they become symptomatic. And then once we've got this virus in our exhaled respiratory droplets, where does it go? So the image you can see is somebody singing, and it's measuring carbon dioxide exhaled from their breath, just as a trace to show where their breath goes. Now remember, smaller particles will follow that, but the big particles won't. And you can see that the breath behaves like a jet, and as it gets to about 30 to 50 centimeters from the person, it then starts to disperse into the air. It gets carried upwards because the breath is hot and it's a humid plume that starts to get carried upwards, but how it moves at that point will depend on the ventilation. How far this jet goes depends on the activity. So if you're breathing gently, it doesn't go very far, and a lot of it gets trapped within your own thermal plume and just travels up to the ceiling. But a cough would project far more than even somebody singing here. So I think we need to really think about where breath goes in environments and thinking about what that means for being exposed to people. And that starts to think about close range exposure. So when you're very close to somebody, you are potentially exposed to all of the different particle sizes. So even those ballistic droplets, which are quite rare, but they can hit you directly in the eye or directly in the nose, but you are exposed to the very large aerosols as well as the very small ones. And the image actually also illustrates why masks matter, because it shows that actually those masks, even a fairly simple surgical mask, will block a lot of the larger aerosols. So we're only then dealing with the smallest ones, which you know, it will significantly reduce the risks. We then need to think about distance, and although distance is not the only thing that matters, it is a very significant part of this, because as that initial trajectory of aerosols and droplets gets dispersed, the further away you are will reduce that risk. And at very close range, you've got a high probability of exposure to all of the sizes of particles, whereas again, once you get further away in the same room, you've got a smaller probability of exposure to those large particles. And once you get beyond about 2 meters, normally your exposure is then determined by the ventilation in the room rather than the proximity. I also want to mention dose response. So this might be a concept that some of you have heard of or might not, but essentially we talk about infectious dose as if it's a, you know, there's a magic number that you're exposed to a certain number and you get infected or not. It's not quite that simple. We actually have what we call it's a dose response relationship, in that if you're exposed to a particular number of viruses, plaque forming units, we often call them PFU, you might be, it's a probability that you would get infected. So we often talk about the 50% probability as being the infectious dose. How much you're exposed to depends on a whole raft of human and environmental factors, so the concentrations of virus, the duration of exposure, and your behaviour. But then whether you actually go on to be infected and your risk depends on what you've been exposed to and the dose response in your body. And that might also change with the variant of the virus. So we know that the Delta variant, which is the one circulating in the UK at the moment, and it's very heavily circulated in India, that one is more transmissible, and we think that part of that is that it might be a lower dose response relationship, so it would be basically less viruses to cause the same infection. This will also change with vaccination status, and we don't quite know yet exactly how that works. Even when you are infected, the consequences will depend on a number of things. So vaccination status, particularly, you can still become infected, but the chances are you won't go on to have such severe disease. But then that will also depend on your health status, your age, and underlying conditions. And it might also depend on how much virus you're exposed to. So there is some suggestion that if you're exposed to more virus, you're more likely to go on and have severe disease. What we don't know yet is what this dose response is. And I've shown two other viruses on the graph. The red one is a human coronavirus called HCOV-229E, which is a common cold type one. And the other one, the blue line, is the original SARS from the 2003 pandemic. And if you look at the graph, you can see that the 50% risk, there's an order of magnitude difference between those two viruses. And that's significant, very significant. We don't know whether SARS-CoV-2 sits closer to the red line or closer to the blue line. I think we're suspecting it sits much closer to the red line because it's very transmissible. Okay, I want to just, that's the sort of basics around transmission. I'll jump into some of the control measures, which will go into how we introduce Frank and Andrew. So first of all, I want to flag the hierarchy of risk controls. And I think this is a really important part of thinking through how we mitigate transmission, in that it's a very standard concept in risk management that, you know, the measures at the top of the pyramid, or the base, I suppose, elimination and substitution, are more effective than the ones at the bottom. And essentially, if you can prevent people getting together in the first place, you are more effective at reducing transmission than if you're reliant just on human behaviour and PPE. And engineering controls sit in the middle of that, and they're the one that people tend to forget about. They tend to skip from work from home to cleaning and testing and PPE. But those, I think, to us are the really important ones, and they're the ones that, particularly things like ventilation, are going to be our long-term mitigation measures, not just for this disease, but for future pandemics. The other point is that the mitigations must cover all of the transmission routes. So although there is differences between the effectiveness of different mitigation measures, if they don't cover the transmission routes, we haven't dealt with it all. So if all we're doing is cleaning surfaces and cleaning hands and putting screens up, we haven't dealt with the air inhaled route. So we have to have something that covers everything. Just to very briefly talk about some of these, I know Andrew's going to talk much more detail about masks, but to just illustrate that masks do a number of different things. They reduce the amount of virus that's exhaled in the first place. They produce protection, a certain amount of protection, depending on the quality of the mask, to the person who's the recipient. And they also change the flow behaviour. And if you look at the video, you can see that when she coughs, the mask completely changes how far that plume goes. However, we know that this depends on the design, the quality, and the wearing of the mask. And there's a very strong behavioural element to this, as well as the engineered design of the mask. Screens are being seen as a major mitigation in a lot of places. I think we need to be cautious with screens. I think they have a role, particularly to block large droplets when somebody is face to face, and they probably also reduce surface contamination in the same way. But if they're too far away from the people, they're not very effective, because essentially the droplets drop onto the surface before they even get to the screen. And then the big challenge is the aerosols go around them. So aerosols are not prevented by screens, and they can potentially cause greater risks. And the image on the right is a computational fluid dynamics simulation of an open hospital ward on the top and a partitioned hospital ward on the bottom. And what you can see is that the partitions change the airflow patterns in that space. And what you will get then is, if it works with the airflow, they can be quite effective. But if they work against the airflow, you get pockets of higher risk in certain areas. So any bringing in screens, it's really important that the airflow is considered alongside the design and positioning of a screen. And then ventilation. Frank is going to talk a lot more about ventilation. We know that there is some outbreaks associated with poor ventilation. We're starting to see evidence of room-to-room transmission, particularly in quarantine hotels, which is quite probably to do with pressure differences between rooms when people are in neighbouring rooms for long periods of time. Ventilation only deals with what's longer range, so it deals with what's beyond about 1 to 2 meters. When you're at close range, the ventilation doesn't deal with that. And it's not simply a case of just a simple linear relationship between saying increased ventilation, reduce risk, because there are a whole raft of other factors in there as well, including duration of time, the size of the room, the activities that are happening in that room, and the breathing rate of the people. I think one of the things I would suggest is that if we're looking at ventilation, I think it's far more important to deal with spaces that have poor ventilation than it is to deal with spaces that are already reasonably well ventilated and try to improve them even further. So putting our efforts into the really poorly ventilated spaces. We can look at some of the ways to model this. We can look at using mass balance models to look at the risks of exposure under different settings under different circumstances. And just to show you an example from some of these types of modelings, we looked at assessing the relative risks between different types of spaces. So we've got classrooms, offices, coffee shops, supermarkets, gym, and some outbreak scenarios in here. And actually, it's not, again, as simple as the ventilation rate, it's the duration of exposure, the size of the space, etc. as well. So, for example, the supermarket in this model comes out really quite low, and that's simply because it's a really big space. So you've got this sort of reservoir effect of a big space, and people are in there for a short duration. Whereas offices and classrooms come out higher just because people are there for 8 hours a day. Or 6 hours a day. And then the ones at the very end, which are a choir outbreak and a German meeting room outbreak, those are much higher because you've got small spaces, poor ventilation, long duration, and continuous activity that enabled that transmission to happen. We've seen a lot as well about CO2 monitoring, and I wanted to touch on this. So CO2 is in people's exhaled breath. Essentially, it gives you a percentage of air that is rebreathed, it's been breathed by somebody else. But CO2 is not just a magic number that represents infection risk. CO2 will increase as people with increasing occupancy, it will increase as people are more active, and it decreases as you increase the ventilation rate. And the graph on the right shows a mechanically ventilated lecture theatre. The black line is your CO2, the pink bars are the occupancy, and you can see a very nice trend in there because it's a very well mixed space where your CO2 increases as the occupancy increases. As we reduce the occupancy, you get a decay to a new steady state, and then as you decrease it again, you get another decay. So it's a very useful proxy for ventilation and occupancy, but it's never a direct indicator of infection risk, and we must remember that. It doesn't tell you directly your exposure to virus. I think CO2 monitoring is a really valuable tool that I think we probably ought to be using more widely in buildings. And it isn't a mitigation measure in its own right. It enables the ventilation mitigation to happen. And it can be used in 2 ways. It can be used by, say, a facilities team to identify poor ventilation, so to go in and measure over a short period and identify whether a space needs mitigation. Or it can be used by occupants, particularly in naturally ventilated spaces, to actively manage the ventilation. So to open windows or change ventilation settings in response to a CO2 concentration. Again, there's no safe value. We can't put a single number on it, but I think looking at the balance of data that's out there, spaces where it's below 800 parts per million, normally, we would like to say those have probably got adequate ventilation. And if spaces are routinely above 1500 parts per million, that's a chance that really says it's probably poorly ventilated and you need to do something about it. If it spikes above for a few minutes, it's really not a problem. It's when it's there routinely and sitting above those values that matter. And we have to remember it's an approximation. It's not an exact number. It's not a regulatory number. It doesn't measure ventilation rate. It gives you a marker for what the ventilation is likely to be, but it depends on your sensors. So you always use NDIR sensors, depends on where you position them. It will depend on the design of the ventilation in there. It will depend on background concentrations. So urban spaces will have higher values than rural spaces. And then it depends on what the people are doing in that space and who they are. Lastly, the hands and surfaces. I said we don't know an awful lot about this. I think we shouldn't discount it as a mechanism of transmission. It's very hard to actually detect it and measure it. And it depends on an awful lot of parameters. But we do know that infected people have quite contaminated hands. And we do know that contaminated hands is a marker for infection risk. So it is part of it, but we don't quite know how yet. I think when we start looking at mitigations, though, providing mechanisms for good hand hygiene and reasonably regular cleaning of high touch surfaces are going to be far more effective than spraying down whole buildings, deep cleaning of spaces, etc. So focus on the hands and the places that people touch, not just deep cleaning the whole environment. Lastly, just want to mention about different types of risks. So it's very easy to focus on what the individual risk is, but actually we need to think about how this all plays out for a population. So let's think about distancing. If we go closer together, that increases an individual risk. But also, when people are closer together, you can have more people there in a space. You know, you can get more people in your restaurant or your office or whatever. If we go from a spacing of 2 meters to a spacing of 1 meter, that means we can, in theory, get 4 times the number of people in that space. That means we've got 4 times the chances of somebody infected being there and 4 times the number of people who can be infected. So if that virus transmits in the air by through aerosols, that increases your probability of infection by 16 times by just reducing that distance. So that's really worth bearing in mind. And it's not, the individual risk is pretty similar, but it's the population risk and it's the consequences. So even if we put masks on, we've still got a higher risk there, perhaps 8 times the risk. The more people get infected in one go, the longer then the onward chain of transmission is, the more secondary cases you've got, and the bigger the cluster outbreak is in a neighbourhood. So I think really worth thinking about actually some of the things we might do. We think that's a small risk. We can multiply those risks up. And so, you know, just reduce that simple act of reducing distancing could change our likelihood of having a super spreader event. So when we're thinking about mitigations, as well as thinking about individuals, we want to think about what's going to have the biggest effect on the population level spread. And I think adapting our measures with the prevalence is going to be critical as we move forward. I think we still need to be thinking about, can we restrict the number of people in settings, particularly indoors? Vaccination is a huge measure in here, which is probably, it's the only real answer out of this whole thing. But then we want to be starting to think about background measures. So good ventilation on the whole reduces that population risk as well as the individual risks. Having outdoor activities again works in there as well. And then things like testing and limiting duration of interactions again will reduce that population risk as well as the individual risk. So just to finish up then, what do we know? We know a lot, but there's still an awful lot we don't know. So I think we know that when you're in close proximity to an infector, that's probably going to give you the biggest exposure to virus. It makes an awful lot of sense, and it's certainly borne out by a lot of the data. There is, I think, the evidence for far-field aerosol is not disputed anymore. We know it happens, we just don't know how frequently it happens. And it definitely matters when you're exposed in a setting for a longer period of time. I wouldn't discount the surfaces. I think they're unlikely to be the thing that's driving a pandemic, but I think they may matter, particularly when you share a space like a shared office or a household with somebody who's infected. And if we want to mitigate this, we have to think about all of the transmission routes. And probably the most important thing we can do is to try and prevent somebody infectious being in the premises in the first place. But we still need an awful lot more evidence. We don't know, for example, viral load, we know something about its variability now. We don't know how vaccination affects that. We don't know about the size of aerosols that contain the most virus. That's still uncertain. We don't know the dose response. We don't know whether different routes of infection change that. And it's actually quite hard to be able to weigh up the impact of different mitigation measures. You know, we can't say yet, is ventilation more effective than hand hygiene or masks? We just don't have that ability to do that. We can model it, but that's an assumption. We don't have the ability to understand it from the epidemiological perspective. And as I say, thank you very much. And that brings me to the end of my presentation. I'm sorry I've gone a little bit over time there.
No, not at all. Thank you, Cath. We have time for a few questions, and there are 3 on the chat. And if you could ask your question, please. I've opened up everybody's mic and video. So if you, yeah.
Yes. Hi.
Question. Yeah.
Yes,
right.
I was the second person, but if it's okay, I'll just.
Yeah. Please go ahead. Right.
So, hello, and thank you very much. I just had a quick question regarding UV light. I understand at a certain distance it can destroy viruses at a wavelength and exposure time. Have you seen any actual scientific evidence that this can actually be replicated effectively in destroying airborne viruses?
Yes, so yes, you can use UV. So UVC irradiation, which is at 254 nanometers, that is well known as being able to inactivate microorganisms. And although the direct evidence on this virus is limited, I think it's a very reasonable assumption that it will do it because it does every other virus in the same way. So, but there are a number of different devices out there. I think Frank might touch on them briefly in his presentation, but essentially you can have upper room UV devices, or you can have UV in an air cleaner type, a standalone box. The question you then have is, once you've got the device, providing it's a good quality device, it's thinking about how you best position that in spaces. But actually, where you've got a poorly ventilated space and it's very hard to improve that ventilation, air cleaning devices based on either HEPA filters or based on UVC are probably quite viable options for reducing transmission risk. I wouldn't be too focused on it inactivating surfaces, though. I think you can only inactivate on the surface in an unoccupied room, because you obviously don't want to be exposed directly to the UV yourself, because it's hazardous to eyes and skin. And because of that, I think it's probably more effective to inactivate virus in the air than it is on the surfaces.
I just felt that if the air goes through a device like that, the exposure time will be too short.
It will depend on the device. Actually, it's not that hard to do. So, bear in mind, we're never going to fully eliminate everything. So it reduces risk. Basically, a UV device works to enhance the effective ventilation rate. So it's as opposed to, we're not talking about sterilizing or purifying an environment. That would never happen. But it is actually even a device with lamps in and the air passes through it, you can quite easily get a 99.9% reduction in what goes through the device. It's then you've just got to persuade the air in the room to go through the device. But yeah.
Christian, could I interrupt? Could we just get 2 more questions in?
Okay.
Yeah, it is quite possible. Maybe we ought to have another seminar on UV, but it is perfectly possible.
Sure. Yeah. Mir, your question, please.
Thank you very much, Vijay. I think my question is a bit off. Basically, I was just wondering if there's any scientific way to find out if I am susceptible to a symptomatic infection or asymptomatic. If I get COVID, so will I be asymptomatic or will I be? And is there any research that has been done?
We don't know. We don't know. I mean, we know that people who are exhaling more virus at the early stages of their disease are more likely to go on and have severe disease. But we don't know. And it's really hard to say who will be symptomatic and who will be asymptomatic. I think the younger you are, the more likely you are to be asymptomatic, which is why there is an issue that virus spreads in schools, but the children don't get sick and nobody really knows it's happening. But yeah, it's really hard to say. And when we talk about asymptomatic as well, some people, it depends on what we mean. So some people might say they didn't have any symptoms, but actually they possibly did. They just had some very mild symptoms that they associated with, you know, air pollution or pollen or something like that, rather than the virus itself, because they had mild, they didn't have the classic symptoms of the virus. You're on mute, VJ.
Raymond, you had a question.
Yes, if I may. We saw a lot of pictures yesterday in the press of absolutely packed streets in London. Now, we're thinking of your 2 meter, 1 meter calculation. Does this mean that we should now fear another surge resulting from that?
That's hard to say. So on the plus side, they were all outdoors. So outdoors does seem to very significantly reduce the risk. And of course, what you don't get there is, so people will only transmit it outdoors when they're close together. You won't get that long range aerosol transmission happening outdoors. So that's a good thing. So that reduces the risk. The bit that makes it more uncertain is all of those people had to get there somehow. Some of them travelled together. Some of them will have travelled in vehicles together, which is I mean, vehicles are a tiny, cars are a really tiny space, probably a bigger risk than trains. Some of them will have also gone indoors, gone into pubs and bars and things. And so it's probably, when we talk about events, it's not necessarily the event itself that causes the issue. It's often the associated things that go with it that might cause an issue. And it's really hard to say, but I mean, we might see a spike. We might not, though, because what will happen is they disperse across the country and we don't know where it's happening. But yeah, it's difficult to say.
Thank you. That's very illuminating.
Okay. So thank you, Cath. Are there any more questions? If there are, Phil, would you like to ask?
Yeah, Vijay, if you wouldn't mind, if I
sure.
could ask a question of Cath. Cath, thanks for your very informative presentation. I'd just like to ask a question about the usage of masks. I mean, that seems to be quite widespread in terms of the continued request for masks to be worn. How effective do you think those are at actually stopping aerosol distribution, given the fact that a lot of people seem to actually wear them intermittently, and also they don't seem to fit very well in the large number of cases?
Yeah, so it is. I mean, the behaviour bit and the fit and things like that is the biggest challenge with that. In that, obviously, if people aren't wearing them, then that doesn't do anything.
No.
I think even a surgical mask which doesn't fit perfectly will have some benefits, though, because it will block the particles on emission. So as a source control, they can have quite a lot of benefits. And one of the reasons there is that the particles that become small aerosols and create the long range airborne transmission, a lot of them start life as bigger particles and they evaporate very rapidly when they leave the body. Mm-hmm. By having a mask on, you've maintained that high humidity environment around the mouth, and you've put a barrier right in front, so they can actually catch some of those particles before they evaporate and become small. So it potentially, even a reasonably, as long as it's got a reasonable fit and a reasonable quality, they will probably have some effect there. What it's really hard to do is to work out what that effect is, and people have tried to do it at population level, and the estimates range from it having about a 6 or 7% effect up to about 45% effect on transmission, and we just don't know what that is. But I think all of these things, we have to add up all the little bits. I mean, hand washing, for example, there's evidence from other respiratory viruses that it's around about 15 to 20% effect. It's a small effect, but if you add that small effect up right across the population, you get somewhere. And I think the same would see with ventilation. I think, you know, if you go from a model would show, if you go from a really poorly ventilated space to a reasonably well ventilated, it's about somewhere between 50 and 90% reduction. But we know that most places aren't that extreme, but maybe we could expect something in the sort of 50% out of ventilation. And if we did that everywhere, is that enough to actually stop it spreading quite so much?
As you say, it's a contributory factor, and it's all part of the layer of protection that effectively we add as part of dealing with the virus. Yeah.
It's also worth noting that a mask actually stops quite a lot going on surfaces as well, because it does mitigate all of the transmission routes, but we just, we can't wear masks forever.
No, we can't. That was sort of where I was driving. How much longer are we going to have to wear them going into the future in order to actually to control the virus? Yeah.
Although I do think actually moving to more
thank you, Cath. Thank you.
Yeah.
Wear them for if you've got a cold, wear a mask is probably quite a good thing.
But thanks for the extensive response, Cath. Okay.
Thank you, Cath. And we've enjoyed listening to you, and thank you for talking to us. And I know you are on a very tight schedule today, and for you making the time to speak to us has been wonderful.
Yeah, thank you very much.
We are now going to move on to our next speaker, Frank Mills, and I did introduce you. What we will now do is that Frank and Andrew will follow each other, and in that period, I'll put off your mics and videos, and I request you all to do that as well, because it will help transmission of the talk a bit. And Frank, the floor is yours, and if you could try and keep it to 25 minutes instead of 30, it would be very good. We're just running a little bit late.
Okay, thank you. Good. Vijay, can you see my slide on the screen?
I can see it. I hope the others can too.
Good. Yeah, we see it as well, Frank. Yeah, thank you.
Okay, thank you. My name is Frank Mills. I'm fellow of the Institution of Mechanical Engineers. I'm chairman of the Construction and Building Services Division, which obviously looks after buildings and, amongst other things, ventilation in those buildings. So I'm going to do a presentation today talking about the engineering interventions we can make to reduce COVID risk. So my agenda today is obviously coronavirus is COVID-19, which follows on from what Cath's been telling us. I want to touch on hospitals and COVID-19 patients and what we've been doing there. And then more importantly, and the bigger focus really, is the reoccupation of all of our buildings after lockdown. We've had a lot of buildings closed and we need to get back into them. So how can we do that safely? And that really is where we as engineers come in. We look at the buildings themselves and their ventilation systems. There is a certain amount of updating we have to do to our buildings post-COVID, because COVID is here to stay, and we've got to make sure that it doesn't come into a building, an office building or a home or a residential space and spread. We want to touch on competencies and training, which is something we've been talking about at the institution, on how we might help people to learn what to do and apply the right things, and then what kind of resources we have available to help us. So my presentation today touches on human environments and health. We know that buildings are much more sophisticated than they used to be. We put a tremendous amount of reliance onto our engineering systems, but they are complex. They need to be looked after. They need to operate properly. One of the issues with COVID, of course, is that clean air, fresh air, which has no infections in it, looks exactly the same as air with lots of COVID aerosols in it. So we can't see what we're dealing with. We have to know as engineers what we're dealing with and how to solve it. COVID itself is a highly infectious respiratory disease. It causes serious illness and deaths, as we know, and the numbers are awful. It's in the air. So we as ventilation engineers have a role to play here in taking it out of the air and killing it off if we can. Where we've had long shutdowns on buildings, there's other issues, of course. We need to go back into those buildings. They've been empty here in the UK for the best part of a year. We are going to have to recommission the whole building, repair equipment that hasn't been switched on, and systems, check they work, almost like restarting from scratch. And in doing that, we're going to have to apply upgrades to the ventilation systems in some of the buildings, not all of them, to make sure they function properly. When we come to look at infection control, we've got 5 stages really, and I think the first one is to look at it at the source, and that's where the masks come in. How can you stop it being spread from one person to another? And Andrew's going to speak about that. The second one is infection control risk management techniques and equipment, which have to be installed by us engineers. So we look at high risk areas where we know there may be people with COVID, hospitals and other places, and see how we can deal with that. And then we move into ventilation really as a tool that will help us solve that risk problem. Stage 3 is in the communities, and that's where we bring in lockdowns, which are fairly expensive, of course, for any country that applies them, and most countries have had to do that. There's a restriction of activities, a loss of freedom to some extent, limitation in what people can do, how many people can collect in spaces, and then countries closing borders. So that stage 3 communities intervention is a rather onerous one, which none of us have liked, of course, but we've had to do it. And stage 4 is really the finding where the infection is, tracking it down, and then trying to eliminate it. And that's something which is going on in every country. And then stage 5 is how we design for living with COVID, knowing that it's here for a long time. Even when we really do get a grip of the problem and try and get back to normal, we'll still be around, like the common cold or flu or any of these other airborne diseases that we have learned to live with. And in that one, the stage 5, again, ventilation comes in as our tool, which we could use to help us overcome it. So we know that infections like COVID are spread through the air. There's lots of infections spread that way, of course, but COVID has come along and it's one we don't really have a cure for, although vaccinations are proceeding, but even people who are vaccinated can catch it and they can spread it, and people can spread it without even having it. They can carry it on their body, on their person, or even in their throat, and it may not particularly affect them. That's the asymptotic carrier, but it's still spreading to other people. So how can we use our heating, ventilation and air systems to stop it spreading? We can, of course, spread it if we allow our systems to pick up COVID in the air and then flow down through ductwork. We can distribute it all around the building. So one person entering at one point could spread it everywhere. So that would be disastrous. So the advice really there is to make sure we don't recirculate air at this time. And if we do recirculate it, then we really have to clean that air. We can clean it using HEPA filtration or UV air cleaners, as somebody pointed out earlier on. But if we aren't doing those things, then we should not be recirculating air at the present point in time, because as soon as a COVID infected person enters the building, that will then get spread through the systems around the building. So switching to full fresh air has been a onerous thing. Of course, it costs us more in terms of energy. We have to heat that air up in winter. We have to cool it down in summer. HVAC engineers control the indoor environment and therefore some of these factors. So we've got the ability as engineers to make a big difference here. We know, as Catherine said, that COVID is spread by droplets and aerosols that leave in the mouth and the nose and enter in the airspace. And we know that large droplets above 10 micron tend to fall locally within the source area. However, the smaller ones are aerosols. They really drift along in the airstream. They can drift down corridors from one room to another. They can be picked up in the ductwork system and distributed through the HVAC system. And don't forget, of course, large droplets can become small because they evaporate moisture and they stay floating in the air. So stage 1 is masks, and I won't go into this in too much detail, but certainly you can have these slides to look at. And my colleague Andrew is going to cover this in a bit more detail later on. But when we look at the engineering infection controls, we realize, of course, that we have a big role here as engineers. We have the medical professionals on one side looking at patients and how to keep them healthy and well, how we can help them recover from illnesses, and not just COVID, of course, but people in hospital need to be protected from COVID, even if they're in for other treatments. And then we have our building operators who are looking at running these buildings and making sure they kept safe for people. But we as engineers sit at the top there, and we can introduce effective ventilation. We can use UV, ultraviolet light, to kill any bacteria or viruses in the air. And then we could use filtration, usually HEPA filtration or a good standard of filter, maybe an F7, which can remove these particles and hold them in the filter. And then at some point, that filter can be removed and disposed of as a biohazard, and then replaced with a new one. And then there's some evidence that controlling relative humidity is another way of reducing the risk of viral spread, although that's not commonly used at the moment. When we look at ventilation, we've got a choice really of natural or mechanical. We ventilate, of course, for air quality, but other things as well: thermal comfort, air movement, and of course infection control. This is a picture of a hospital application. In the UK, we do use natural ventilation, but we limit it really to ward areas, which for a typical UK hospital could be up to half the rooms in the hospital. But anything where we're doing clinical work or medical work, they would be sealed and mechanically ventilated. And of course, the HVAC systems then would have these features that I talk about. But even the naturally ventilated areas have to have effective ventilation, which would reduce any COVID risk. So treatment areas, and people can see these numbers in our hospital guidance, NHS HTM03. Treatment areas need 10 air changes. So it's quite a high air load, quite a high cost, of course, to supply a system that will deliver that. But at that kind of air change rate, the dilution effect is such that we could keep COVID down if it was being admitted into the air there. So 10 air changes just, of course, in simple terms, mean that every 6 minutes we replace the air in the room. Now, of course, because the air is mixing all the time, that's not what happens. What actually happens is we dilute the air. And so at a rate of 10 air changes, it would take around 28 minutes to actually replace the original air. So it's a case of keeping the dilution factor going. And in more important areas such as operating theatres, we work to much higher air change rates, typically 20 or 30 air changes an hour. So effective ventilation is an important principle to understand. We certainly need adequate ventilation in areas, and we have references to those in our guidance documents, as you know. But I suppose the hospital guidance is the only one to date that really look at infection control, where if you take a commercial office building, we're concerned with health and well-being, of course, but up to this date, we've never really been concerned with someone walking in with an infectious disease. So we're now having another look at those kind of rates and seeing whether we need to change them. So certainly the advice at the moment is ventilation rates should not be reduced if occupancy reduces. We need to maintain good rates that mitigates any risk of airborne transmission. In other words, it maintains that dilution rate with whatever air change rate we have. We want to increase the fresh air rate if we can. So if there's anything we can do to our systems to get more air through, we should do that. There's quite a lot of additional advice there on the right-hand side of my slide, where you can look at filtration. Adding filtration is certainly one way of removing particles from the air, but we have to check with our design that the air handling plant we have, the air handling unit, has enough fan power to actually deal with a higher rate of filtration. So it may not be that easy. Or we could put ultraviolet air cleaning in the ducts. That doesn't tend to have too much resistance to flow because there are gaps between the lamps for the air to flow. There is some resistance, but it's not a high one. But that then has to follow a particular procedure. And I've quoted the ASHRAE site here, and you can have a look at that. If you do use ultraviolet light, it's probable that you can stick with the filters that are in at the moment, because the filter is really just, well, I suppose in my term, keeping the lamps clean. It's not trying to remove the virus, because the UV is going to do that. We could look at adding humidifiers in dry climates, and we could disable demand controlled ventilation. This is where you may, on a variable air volume system, change the amount of airflow depending on how many people are in the building. But during this pandemic mode, our advice is not to do that, to maintain the full airflow rate. And then there's the idea of introducing flushing periods. So before people come into a building, we would bring the ventilation on for a couple of hours and flush the building. And after everyone's left, to go home at night, we would flush it again for a further 2 hours just to remove anything. But we, as engineers, need to have a look at those buildings, and we may decide that the ventilation system that's in is not appropriate, and we need to either upgrade it or even change it. So we were talking about measures to mitigate, and ultraviolet is certainly one of them. So outside the building, relatively safe, as Cath says, because there's plenty of fresh air for a start. The ventilation rates outside are very high. And also UV is going to kill any virus or bacteria that are around. So there's various studies on that, and I quote them there. And then there are these options. There's 3 basic options as shown in this slide. We could put the ultraviolet device in the ductwork as shown there. So as the air goes through the ducts, it goes through a box with ultraviolet lamps in. Now, I should say at this point that ultraviolet is very harmful to a human being. So we don't want the UV light shining either into your eyes or onto your skin, because it will create problems. In fact, it creates cancer. So it has to be hidden away. But as the air flows through that box, it is sterilized and comes out the other side much cleaner. Not necessarily 100%, but probably around 99%, 95% cleaner, depending on the application. The other options here are to put the ultraviolet light into a box in the ceiling, and described here as a ceiling jet. So that picks the air up from the room, passes it through the box, and then blows it back into the room cleaner. And then the third option, just shown on the bottom left-hand side, is the mobile unit, where we could stand a box in the room somewhere in the corner, and that could draw the air in from the room, pass it through the UV lights so that it's cleaned, and then put it back into the room. So there's 3 types of application there as shown. And this is a picture of one in a piece of ductwork. Of course, that's above ceiling, maybe in a plant room, and put it where you can fit it. Bearing in mind that you'd have to modify the ductwork to get it in. It requires an electrical supply, of course. You need to have access there to get into the unit to replace the lamps regularly, because the UV lamp has a life of about 13 to 14,000 hours. So that's typically every 18 months you'd be replacing those lamps. And you need to have various safeguards on that. So once someone is working on it, the unit itself is dead, the lamps can't be turned on. The ceiling jet unit that I indicated there is shown on the left in that picture. And on the right hand side, you can see a diagram of a room where it's pulling the air up, drags it in through the unit, the UV lights inside sterilize the air, and then that air is blown back into the room as clean air. And that application I'm showing there is a mixing application. And then the third unit I showed you was a mobile, and this is one in a hospital in the UK. It stood between those 2 beds there, as you can see, and it's about 1 meter high, and it draws air in at low level, which is the right level, by the way, because these aerosols and droplets tend to drop down to floor level. They tend to be a little bit heavier than normal air, so the unit pulls them in and then blows them back out as sterilized clean air. So it's helping to dilute the air in the room, but if you position it properly, you can also use it as a clean air screen, of course. And just having a look at this, we've been doing some work with the NHS here, and we think that we need a decent filter in it, such as a G4. The job of the G4 filter is to keep the lamps clean. The G4 will take out particles, of course, but it's not trying to remove the viruses. The virus is very small. They be on particles down to 3 or 5 microns. But the G4 is keeping the lamps clean. We don't want lamps getting clogged up, or the UV won't be active. The UV lamps deactivate about 90% of the viral content. So by continuous reprocessing of the air, we can get that room relatively clean. So that's a shot through a typical mobile unit, showing you what's in there. And now there's plenty of information around, which I've put in the references at the end of this talk, but probably one of the most comprehensive is the ASHRAE Handbook, Chapter 62, ultraviolet systems. That's quite a good source, and it tells you exactly how ultraviolet does the job of sterilizing air, because it's killing bacteria and viruses. So some people would say viruses are not actually alive, but I'm using the word there as an engineer to say I'm eliminating it, deactivating it, or killing it, whatever you want. But the UV is harmful to humans, so we need to shield it from people at all times. Its performance depends on the intensity of the lights from the lamp. And also, as Cath said, it really needs to be at that frequency of 254 nanometers. So LED lamps are not, so I just go back to LED lamps are not really there at the moment. They're around 220 nanometers. So we're still using fluorescent, but the 254 gives us the peak intensity. And then it needs some dwell time. It is no good just passing it straight across a lamp. It needs to be there long enough to deactivate. So it needs to be close to the lamps and at the right kind of speed. If it's too fast, it doesn't work. And these are a summary of those points. 254 for maximum effect. Fluorescent lamps are things that do that. LED lamps, which you will be offered and you can use if you want, but they're only at 220 nanometers and they're less effective. Fluorescent lamp life around 13,000 hours. Use a G4 filter. Dwell time important, of course, and the distance from the lamp, and that was a question earlier. You need to be under 100 millimeter, so the lamp is really not going to do too much if you're a couple of meters away from the air you're trying to clean. So the unit has to make sure that it directs through with passageways which are less than 100 millimeters, so the air is cleaned. The UV intensity needs to be quite high, 3,000 microwatts per centimeter squared. And as I say, if we can draw the air in at low level in a mobile unit, we've got more chances of catching in the particles that we're worried about. So there's a reference there to the work by Professor Kowalski, who has really been the pioneer of using UV, and there's references to his work on at the back of this presentation. It's a good idea if you have any of these units to know how long they've been running. So have a meter on it or a BMS connection that tells you the UV unit has been running for 10, 11, 12,000 hours, 13,000 hours. You know it's about time to change the lamps. It should have a lamp fail signal as well. So you know that it hasn't worked, because it could look like it's working, but it's not doing any work, then you have a dangerous situation. So get some lighting on the unit, which gives you that. Now, here's some work we've done in the UK in dental surgeries, where we have a particular problem with people, obviously with their mouth open, generating aerosols, with a dental nurse in and a dentist. And in this particular application, we're looking at a swirl diffuser in the ceiling there. We replaced a mixing diffuser with a swirl diffuser to throw air down over the chair. And what we wanted to see here was whether we could control the air movement better. As you can see, this is a live presentation we did. So sorry, we're talking while we videoed this, but you can see how the air from that is blown downwards. So it's clean air coming down over the patient, and therefore we can protect the dentist and the nurse either side from that. And then we'd replace that with this type of diffuser, which is a nozzle jet diffuser. And this has about a 10-degree offset. And the reason for that is that in this particular dental surgery, the room is not square, it's not really oblong either, and the chair is not in the center. So we needed to control the air movement sideways. So this is a diagram which illustrates that happening. The air is being thrown off center by about 10 degrees, which is directly over the chair there, which is where the patient is. So it's blowing any aerosols that the patient generates downwards onto the floor. And then over at the back of the unit there, we have a mobile UV air cleaner. So this is a hospital application with clean air coming from the ceiling. Unfortunately, what we've found in this situation is the air change rate was only 5. We should have 10, but we have 5. And you will find this, as engineers, when you go out, that the air change rates don't comply with standard anyway. So moving on, we could also use high degree filtration. So air filters can certainly remove viruses. So a HEPA filter unit, and that could be in a box unit in a room can remove particles at 99.97%, down to 0.3 microns. That would take out most bacteria and viruses. However, just bear in mind the viral load you've caught is actually trapped in the filter. It won't die off by catching it. It will die off at some point, of course, but it may be active for some time. So you've got to be very careful when you replace that. You certainly wouldn't replace that with anybody in the room apart from the engineer or technician who's replacing it. So if it's a ward application, you'd have to empty the ward that day, or take the unit out of the ward if it's a mobile and do it somewhere else. During filter changes, say, treat it as a biohazard. I just want to touch briefly on humidity. Dr. Stephanie Taylor, who's based in Boston, has quite a lot of work claiming that infections are low if we keep the relative humidity between 40 and 60% RH. And this diagram illustrates that. This is also repeated in the ASHRAE publications I referred to. At the moment in the UK, we don't really do much in the way of humidity control. It's a fact that our particular climate tends to be in that zone most of the time. But bear in mind, of course, we're talking about in buildings, so we could have situations where we get a higher humidity due to moisture generation from people, and in winter we may get humidity down to 20% on very cold days, of course. But we then have to do that risk assessment, whether it's worth spending a lot of money and a lot of technology to get into that zone. But certainly in some areas and some climates, it could be a real problem for us if the humidity is maybe in a 20 to 30% band a lot of the time, or up around 70 to 80. We could find more spread. So stage 3, moving on from those, would be the communities lockdown, which I referred to earlier, and this is really done by government, not by us. And then move on to reoccupation after lockdown. So once the government decides we can go back into buildings, and we're sort of been given that instruction now, we need to make sure they're ready for people. So we've got to look at risk assessments, got to look at behavioural changes we can introduce. For example, do we allow everybody to get back into a lift, or do we say that the lift can only be inhabited by 1 or 2 people at a time, because we don't want a big crowd in the lift in case someone with COVID enters that lift. We need to clean, repair, check, and possibly recommission all of the engineering systems serving the building. And then we need to take some additional steps, which might involve bringing UV air cleaners in, or HEPA filters, or maybe changing our air handling plant operation as described earlier, or even upgrading the ventilation system to provide better protection. And then we need to make sure that our maintenance procedures keep these things working properly, because now we're relying on them to avoid COVID spread in the building. So the risk to us would be that we get sick building due to build-up of dust and dirt in the building, maybe a failure of plant and equipment. There's obviously security, fire issues. There's certainly quite a lot of energy wasted at the moment because we're on full fresh air. So maybe we want to bring in systems to deal with that. And then we have to look at that issue of an occupant arriving with COVID causing problems. So that really leads me to the conclusion of my talk, which is talking about how we might design for living with COVID. It's here to stay. Obviously, lockdowns are expensive and unhealthy. How do we reoccupy buildings? And we're starting to see these designs coming through now. This is a building in Chicago, and as you can see, they're claiming this is the first post-COVID-19 structure designed with enhanced air filtration, much more widely spaced offices, and other touchless features, so that we reduce the risk of COVID in that building. So this is where the property market is beginning to go. And of course, we also need to educate and train people, and particularly engineers, to make sure that we can deal with this. So the IMechE, and I won't go into detail here, but we are looking at CPD systems where we can offer training which would give a badge of recognition, a competency certificate, in fact, to engineers who are knowledgeable in this area. And we would call that person an infection control engineer. He's qualified, he's got experience in ventilation, and he really understands the science behind COVID. I just want to conclude by showing you a list of references which I've attached to these, and no doubt you can have a look at those later on. But certainly go on our website at the IMechE and you'll see these. So with that, I'll conclude and ask us any questions. There's my email.
Thank you, Frank. It's a very fine talk that you've given. I'll just get Andrew to give his talk too. And
Okay.
then after that, we can take a joint session on questions. And Andrew, you have about 25 minutes or so. Thank you.
Thank you very much. Thank you. Right. Hopefully, just a moment. Just getting the presentation ready.
Frank, I think you have to withdraw your presentation. Yeah, that's right. Okay, that's fine.
Yep. Okay, good. So I'm going to talk a bit about masks and controlling risks. So what I'm going to cover, hopefully you can see the presentation. We're going to talk about masks and controlling risks, looking at a risk approach to infection control, an example of a risk approach, and then talk about the key characteristics for control of COVID-19, and that's very much building on from Cath's talk, and then talk a bit about masks and how they operate. So first of all, about risk. Now, most of us are familiar with the idea of the Swiss cheese model of risk, where you have a hazard, you have various controls. I've shown here with engineering controls, administrative controls, behavioral controls to prevent the incident, but each of them have a weakness which you could end up with an incident happening. And then you can have some mitigation barriers to reduce the consequences of that incident if it happened. And if we think of it in COVID terms, we think first of all of the COVID transmission is the actual incident. The engineering controls, we've talked about ventilation, there can be physical barriers, screens, we can apply filtration, air or surface sanitizers, and antimicrobial services are all ways that we can reduce the likelihood of that incident happening. Administrative controls, we can put in cleaning routines, we can put in labels to direct people, we can have workplace testing and temperature testing, all ways at trying to reduce the likelihood of that. And in terms of behavioural controls, we can put in mask wearing, the social distancing, we can make sure people have reduced time exposure, but by asking them to have reduced time exposure, and personal hygiene aspects. In terms of consequences, which might be short-term incapacity, death, or long-term incapacity, all consequences of having had COVID transmitted. And to reduce the impact of that, the consequences, we can look in detecting infections. We can make sure we understand when people have got it. We can isolate, we can monitor blood oxygen, use drugs, oxygen or ventilators. So all ways they can use those. So if we think of an example of risk, this is IATA, the International Air Traffic Association, and they've put together a way of how airports can deal with, and airlines deal with risk. And first of all, it's informing passengers to be ahead of time, be prepared ahead of time by online check-ins, completing the forms of visas, travel authorization, contact health information ahead of it, printing and attaching e-bag tags, asking them to have enough masks and hand sanitizer for the entire journey, and compliance with testing protocols that might be there. That's before they arrive at the airport. When they get to the airport, they'll be looking at temperature screening. There's potential for that as they come into the area. Having self-service check-in rather than having handlers handle bags that may have been infected. Bag drop facility. contactless boarding by mobile device. So these are all various ways you can reduce the surface contact and reduce the potential for queuing. So you have self-scanning boarding passes. Surfaces and trays are being cleaned frequently as they go through X-ray tests, inspections. Gloves used for inspections by the security personnel. Making sure people queue and prioritizing the queues such that they will go through to the aircraft in the right order to minimize when they get to the aircraft, the queuing on board the aircraft. So there's lots of things that people have thought about as to how to prevent close contact and contact of surfaces. On board the aircraft, we have mask wearing. Catering procedures have been simplified to lower the crew movement and interaction with the passengers. Persuade people to move around only if necessary, in other words, just to visit toilets, that sort of thing. And there's going to be deeper and more frequent cabin cleaner. At the arrival, again, minimizing proximity interaction, contactless immigration process, all to minimize that contact, so that we need to think through how people move through processes and how to minimize the contact at each stage, how to minimize the queuing, the close proximity. So that is how to evolve a risk process. And over and above, communication is a critical aspect where we need to ensure people are communicated to clearly so they understand what they need to do. It needs to be simple and timely, that the people receive that information. So getting people emails sent when they're just prior to boarding, prior to traveling to the airport, making sure they have the information they need to be able to operate safely through the system. I now want to switch into building on what Cath has talked about, is the transmission. Here we have the idea that we have particles of the aerosol droplets coming from somebody's mouth. They have a certain velocity and particle mass that comes out. Some of those will fall to the surface, as we've talked about. Others will travel through the air, which will be a function, and how alive they stay or active the virus stays depends on time, the sunlight, temperature, the humidity, and then the distance it will travel. And we've talked about seeing how surfaces can be picked up by hands transferred to the mouth or eyes, and mass can reduce the flow. But the critical thing is when the virus enters the body into the airway, it actually attacks to a certain enzyme, the ACE2 enzyme, which is primarily in the upper airway. So we're looking for particles that get into the upper airway that are important to us. And as Cath was saying, size is a consideration. The virus itself is of the order of 100 nanometers or 0.1 of a micrometer. Hair, I think my hair is slightly thicker than Cath's, obviously, 70 micrometers. And the cells are typically in the region of 10 to 100 micrometers. We refer often to the droplets that are expelled by the humans as being aerosols up to 5 micrometers and droplets beyond there. And there's a sort of perception that droplets fall to the ground and aerosols stay in the air, but in reality it's a continuum of things. And if we'll build on that a little bit later, but in terms of distance, it's shown that actually when you sneeze or cough, you can actually reach as far as 8 meters with a turbulent cloud of droplets. And then after that, they will evaporate, will drift away and disperse with the general airflow. But that initial cloud can travel as far as that, which is sort of 4 people's lengths. The larger droplets will fall out of that, but that we need to be aware that we can have that amount of distance. If we think of masks now, they have three roles, as Cath was pointing out. First of all, that penetration of the cloud of droplets through the air from the infected person, that distance that's travelled. Then they act as a filter to filter out the droplets and aerosols that contain the virus from the infected person out into the environment. And then they have the role of filtering out the droplets and aerosols that are in the environment into the non-infected person. So they've got those three roles that we need to think about. And Cath had shown the penetration effect. Let's talk a bit about the filtration effect. The filters work by larger particles are physically blocked from passing through them. They can't fit through the gaps. When you get to a medium-sized particle, what tends to happen is as the air flows through them, it has to go through a quite fairly convoluted path. And by the momentum of the particles, they don't follow exactly that, and they will collide with the surface of the fabric and will actually attach to the surface. So they don't, even though they're smaller than the holes, they won't actually get through. And then when you get to very small particles, Brownian motion or electrostatic attraction makes sure that those particles will actually touch to the surface of the weave and actually get stuck there. So just the physical size of the mesh isn't the main dictator of how much flows through. And if we look at there's some data here from looking at mask material, looking at the effective size, and you'll see that when we get to 10 micrometers, the particles are behaving that we have a fairly good filtration effect. This is showing as a function of different mask materials. There's this time there's 2 layers of jersey, a silk thin sheet, and a vacuum bag. And then typical of most materials that are used for filtration, they have a minimum filtration effect around between 0.1 of a micrometer and 1 micrometer. And then as the electrostatic effect comes into effect, they actually improve in filtration effectiveness at smaller sizes. The other thing to note is filtration is also a function of the velocity through the material. So the solid line represents high velocity and the dotted line, dashed line, a lower velocity. And that typically swaps over in terms of effectiveness, so that at lower velocities, they're more effective than the higher velocities at filtration for the smaller particles, but at bigger, it's the other way around. And that's because of the different mechanisms that are preventing the filtration. Coming back to the aspect of the continuum between aerosols and droplets, this is a graph which shows the terminal velocity if you're absolutely still air of particles that fall through the air. And as a function of droplet diameter, you'll see that the velocity, as we go down to towards the 1 micrometer, the velocity through the air, is less than 0.1 of a millimeter per second. It's very easy to conceive of air flows within rooms and particularly outside to dominate how much the particles are moved around. Whereas when you get to larger particles, 100 micrometers and beyond, they will fall relatively quickly through air, and similarly the air movement has little effect on those. So it is a continuum that it's just pure physics and computational field dynamics of the particles that will cause the particles to move around. And it's always worth bearing in mind how those particles then will be controlled by the flow of air. It's very simple to think in terms of the flow through a mask, around a mask, will control the direction those particles go in. So Another thing to think about is how far do the particles travel into humans? This is taken from a graph which has been around for many years. It's based on particles that they were observed in the lungs and throat of people, and it's shown that the major part of particles that are present right down in the lungs are very small particles. In the throat, it tends to be a slightly medium-sized particle, so into that range of the 1 to 20 micrometers that are important to get into the chest, into that upper airway where we think the actual connection between the virus and the throat is happening. Larger particles will tend to get to the mouth, but don't actually travel down into the airways. So if you come to masks, there are various standards out there. There's first basic classifications of masks. There's respirator masks, which have been designed to protect the wearer from particles. Regulations define Europe, USA, and in Far East. Surgical masks, which you see as a typical blue mask, which was primarily there to stop large particles emitting from a person getting to the an infected wound or something like that, or causing the potential. Again, regulations defined Europe, USA, and China. There's what's known as a protective mask, which is regulated in China, aimed at pollution protection. And then what has become to me known as the face covering, which we see was set up very much to try and reduce demand for healthcare protection equipment. And the intent primarily is to have a similar function to the surgical mask, stopping those large particles. That was how it started. But it's of note that it's very much unregulated, but there are voluntary standards appearing across the world. So if we look a bit more at the standards, the critical thing to understand is the standards often relate to the particle size. So there's filtration standards and particle size to consideration. And the 3 particle sizes that are considered, and there is a distribution of this around these particular numbers that they're tested for. But primarily the bacterial particulate efficiency, BFE, which is aimed around 3 micrometers. Fine particle filtration efficiency standard, which is around about 0.1 micrometers. In other words, the size of the virus itself rather than the droplets. And there's some tests around the 0.3 micrometers, which is aimed to look at the most penetrating of where those minima that you see in the terms of filtration style. So if you look at the table, typically we see masks from 95% required up to 98%. And this is a test of the material. It doesn't test the whole mask as an assembly. It's just purely looking at the material is how they're tested. And for respirators, the masks that you typically see having a fairly good seal, the material capabilities in the 95 upwards, apart from the FFP1, which is aimed very much at workers rather than thinking of a medical situation where they want a high breathability. So in other words, be able to breathe easily. And so that in that circumstance, they allow for a significantly lower efficiency of 80%. So those are the masks that we've known about for, have been around the standards for many years. Now we're having reusable face coverings, and there's a number of standards which have been put in place over the last year. This isn't comprehensive, and although these standards are out there, they have very limited use in the marketplace as such. A lot of masks have no reference at all to the standards that they may comply with. And it's notable what the people setting the standards have tried to do is set them really below the standards of the medical masks and protective equipment. So the relatively low filtration sufficiency as the standard. They also have very different thoughts in terms of what particle size they should test for. But potentially they may be looking at a longer term usage of these standards, because although coronavirus and some other respiratory viruses are particularly significant in terms of they travel with the droplets, and so the areas of interest are the 1+ micrometers. Some diseases, such as measles, it is actually the very fine particles down in less than 0.1 of a micrometer that is actually important. And they're the bits that, because they travel right into the lungs. So it may be that some of these standards are looking to the future, not just for COVID. But a critical aspect of understanding the filtration performance of a mask is leakage. The air that doesn't pass through the material doesn't get filtered. So in other words, those particles will get into the air. The smallest particles will follow the air rather than ballistically impacting the mask. So as I say, they're very driven by the air. But larger particles will impact the mask, the big droplets. And there's this study which was shown how the effect of leakage, relatively small amounts of leakage, has a big effect on the filtration effect. So even by 1.5% of leakage, you can be reducing the filtration efficiency by half. And there were some experiments that looked at the effect of leakage on using surgical masks, and it's shown that the filtration efficiency from a nominal 98% of the type 2 masks that we used were bringing down into the 50 or less, depending on the subject who wore it and how exactly they fitted it. Still a function of size, so the bigger sizes of particles were still better filtered, but it's showing how much the wearing of the mask and the practical leakage changes things dramatically. And ways to reduce performance. Well, we've all seen some poorer behaviours, not putting it over the nose. Pulling it on and off with the hand, you get the potential for transmission onto the hands. Wearing a mask that is not the right size, not the right shape for your face, can end up with gaps. And then I'm afraid beards, which are this magnificent example, unfortunately the beard is not very good at filtrating the particles, so there'll be a lot of leakage. Also, wearing the mask over glasses will give a leakage area behind the glasses. So there's ways that bad behaviours that will enhance the ability of the particles to bypass the mask. So things that we need to make sure is pulling masks down, pinching on that metal band if there is a metal band in the mask, so as we can get the best possible fit. There have been studies to show how we can improve the fit by reducing the leakage. This was done through the CDC, the American Disease Center, starting from a mask which had a side gap. It then put on a double mask, in other words, a fabric mask over the top, and it showed a substantial reduction in particles that were transmitted. And then they looked at how they could improve the fit of a single mask, a surgical mask, and that was by knotting it and then folding the surplus fabric underneath, which showed that actually that is also quite effective at reducing the leakage and hence improving significantly the amount of particles that get distributed outside the mask and into the next person that could receive it. There are health concerns been raised with masks around oxygen depletion, excess CO2, headaches. Now, in terms of oxygen depletion and excess carbon dioxide through wearing masks, there are seen to be very slightly increased levels of CO2, reduction in oxygen, but it's actually well within the normal human levels. And those effects are self-regulated by normal bodily functions. So they're not a risk to normal humans. If you have somebody who is particularly suffering already, then obviously that's something that we need to deal with and not put a mask on. But people, normal people, will not have problems with that. We are seeing when people wear N95 masks in particular, which are fit quite snugly on the face, that when they use them for more than 4 hours, they have more frequent headaches. But that's likely to be the result of the facial pressure rather than the reduced hydration, rather than the impact of oxygen or CO2. And of course, there are the benefits from reduced particulate intake if there is poor air quality around, and that in itself would reduce headaches and improvements to blood pressure and breathing rate. So do they work? Well, there's been studies of people who share households with a flu-infected person, and they saw that mask usage did cut secondary infections by half. And there's been a couple of studies that both showed that sort of data. We haven't seen any studies yet on COVID-19. There's not the circumstances to reduce that, but certainly we have seen in flu, which is a very similar size of particles that tend to infect people, another COVID type virus, and that has been successful. So some masks have limited benefit. As you can see, the one on the left, that won't stop anything. But in fact could be legal in many areas in terms of satisfying the nominal requirements of the legal requirements. Similarly, clear masks that are a single sheet. The problem is, although it will prevent the prevention of the projection of fluid, the aerosols will entirely escape because all the air that the person breathes doesn't get filtered, and so will escape into the atmosphere. So it's a limited benefit, particularly inside buildings, in terms of stopping that aerosol effect. So in summary, this is engineering. It's all about movement of air. It's about particles, how they move within it. We're used to that sort of thing. It may be that we've looked at it in terms of combustion, mix of fuels in air. It may be that you've looked at it in terms of paint spraying, how paint as an aerosol actually gets onto the surface of things. So this is engineering. So if you think a bit about masks, they do reduce the likelihood of infection in terms of preventing the larger particles in particular traveling significant distances, reducing infectious particles entering the environment and reducing the intake of carbons. But poor usage does reduce their performance significantly. There are ways to improve the masking performance. The health risks are very low from wearing them. So then overall, masks are there, they used in conjunction with other risk reducing strategies, they have a significant role to play. But it is look at the whole picture, don't rely on masks alone. Thank you.
Thank you, Andrew. That was a very fine talk about masks. And we have a short amount of time available for questions and answers to the second and third speakers. So if anybody would like to ask a question, please raise your hand. And I see there has been a set of questions in the chat from Mir, but Mir, I think one of your questions was answered about long-term effects of wearing masks. But maybe you want to ask the other two, or at least one of them.
Yeah, they have, in terms of bearded people, it's notable in the health service. They, particularly where they want them to wear the N95 mask, which is reliant on that good seal around people. They require that the health workers actually have clean shaven around the areas where the mask may come into contact with them. So sort of goatee beards may be okay, but not the full set of whiskers, I'm afraid. So if you want the best performance out of a mask, I'm afraid you've got to forgo on that beard.
So Mir, you've been failed.
Yeah. No, actually, we have to come up with a solution. You know, I think there should be something. So see, and the other question which I had was something, you know, something that we generally face while using mask is, you know, whenever we exhale air, so that thing just stays around, and then when we inhale it, then we'll have to, you know, take it in. So you know, can't we have something, you know, that has separate pathways altogether, you know,
Yeah,
so that, you know, you have a separate inhale path and a separate exhale path? You know, is there anything that has been done, or is that still you know, innovation yet to be done?
No, there are masks which have valves which control the inflow and outflow, and they can be fitted with filters. But the masks generally have been there to prevent dust particles coming in, and they have ensures that filtration is there on drawing the air into the mouth, but they let air out very easily, in other words, not through a filtration route. So they have these valves that control it. Now, the problem with that, obviously, as in an infection environment, you would want to stop the particles going out as much as you want to stop them coming in. So they have a limited role to play, really, in an infection environment. They have used them as some people who you know are not infected going into an environment where there is infection. They have these devices that have allow exhaling of air without a filter in it to make sure the air can go out easily, but then having the filter to come in. But that is only pertinent if you know for sure that the person wearing that device has not got the infection in the first place.
Thank you, Andrew. Thanks very much. I'm afraid we're going to be running out of time very soon, so I'll request that if there are any questions, you could send them to Sean Dixon, whose email address is at the is in the flyer for this meeting, and we'll make sure that an answer comes back to you. So it's my very pleasant duty to thank the three speakers. I think Cath has already left because she had another appointment, but I want to thank you all for coming. I want to thank you all for organizing this event and giving us the benefit of the current state of the art in terms of advice to undertake infection control and give us safe working places where we can live with the pandemic, just as we live with flu. It's not quite that, it's still a killer, but yes, these measures will help, and I hope you got some nuggets of advice which you can use. And I want to thank all those behind the scenes, including our comms staff and our headquarters staff and the IT people who made such terrific arrangements for this webinar. And for all of you for coming on a Saturday of all things, very early in the morning in the UK. Thanks very much, all of you. And now I'll hand over to Mark, who will sum up what happened today, what learnings we have, and after that we'll close. Thank you.
Hi, BJ. Thank you very much for that, and thanks for everyone who's managed to dial in and sort of be part of the call. One of the things that we have been doing is we've been inviting volunteers to get involved and try and sort of expand beyond the usual group of people that have already volunteered. So if anybody that's been on the call today wants to maintain their involvement, then please feel free via Sean to connect with me, and we can make sure that you can contribute to what we're doing. We are at the process at the moment of trying to create a continuous professional development module so that we can expand on the work that the speakers have done today, so that individuals will then be able to go into organisations and to make them safer. Thankfully, in the UK, after many months, the government are now acknowledging that not only is an airborne virus and we need to control indoor air quality, but they're also acknowledging the fact that we're going to have to live with COVID for the indefinite future. So our work is becoming more and more important, and we're reporting to the Chief Scientific Officer to try and come up with some of the advice that we've been giving out today to suggest that our health and safety executive implement controls so that society can reopen. It's as Andrew said, it's the Swiss cheese model that is really important. So fingers crossed for you guys, the people that we were targeting, the people in India. Every area of the world is at a different phase. We're just re-entering a surge at the moment, where at the moment we're doubling instances of infection every week. So it comes and it goes. It doesn't matter where you are. I think we've got to come up with coping strategies for the indefinite future. But thankfully, with the incidence of the vaccine, there aren't as many people who are succumbing to this and who are ending up, in a very serious condition. But very conscious that it's coming up to the 10 o'clock hour. So I can only say thank you for the people that have given up their time to come today, and I really do appreciate the fact that our experts, our film stars in this area have managed to sort of give up their Saturday mornings to share this with our colleagues around the world. And hopefully the recording will be on the website soon, so those that did miss it will be able to pick up at some time. So thank you very much, Vijay. Back to you.
So once again, thanks a lot, folks, and I'll release you from the webinar. Thanks for coming, and I hope you had a good day today. Goodbye.
Thank you.
Thank you all. Bye.
Bye.
DJ. Thank you.
Bye.
Bye.
Vijay, remember to end the recording.
Yes, that's just what I'm going to do. Thank you, Kevin.
No problem.
And I'll download it and send